Babies, welcome back. So what we're going to talk about today is what's called projectile motion. So this is going to be an application of two-dimensional vectors. Specifically, we're going to look at two-dimensional motion. Okay, so just understand projectile motion is 2D motion. And again, two dimensions means that we're acting in two directions at the same time. So what we're dealing with is something called a projectile. A projectile is simply something that's being launched. So we are launching things into the air. So in terms of motion, we're going to look at things that are undergoing free fall motion, but instead of just dropping an object like we did or talked about in Unit 1 or throwing an object straight in the air, we're now going to apply the same idea to two-dimensional motion. So we're going to look at what happens when I throw an object up in the air but allow it to move forward as well. So understand this is two-dimensional motion because not only am I taking this object and throwing it up in the air, but at the same time that object is moving forward. So this is where we would see two-dimensional motion because the object is both moving up and down in the later part of its motion and forward at the same time. So this is going to take into account some of the things we talk about with free fall motion and motion in general, and also take into account some of the operations and fundamentals of vectors like components, the resultants, and then some of the math that we did with Pythagorean theorem and the trig functions. So it's going to be kind of a connection of all things we've learned up to this point. I was kind of explain what's going on here with projectile motion is to think about first going back to motion in general. This is going into kind of combining motion along with Newton's laws. But let's say that I have a cannon that launches a cannonball. And let's say that I were to launch a cannonball. So again, this cannonball that's being shown here, this would be called a projectile. So I'm going to project this thing out into the air. And let's say for now, to make it easy, what we're going to do in this first section is just consider things being launched horizontally. So that means I am launching this object straight out of the cannon, straight to the right. Okay? So according to Newton's first law, what we state is that an object in motion will stay in motion, object at rest will stay at rest. So if I were to think about this motion without gravity, so obviously with gravity, the object would fall towards the ground, but without gravity, this object would continue to move forward. That would show Newton's first law of motion, and an object in motion will stay in motion unless there's any unbalanced forces acting on it. So in this case, the object will just continue to move forward, and as long as there's no forces acting on it, it'll continue to move forward. But we know, okay, based on our study of free fall, that an object that is launched or an object that is dropped will fall towards the ground due to gravity. That gravity will pull this thing down and will cause that object to speed up as it falls down, because no matter where you look, gravity is always going to be pulling this thing downward with a certain amount of force, and that force will always be the same. So what projectile motion is kind of a combination of these two. That imagine a motion without gravity and imagine a motion just falling straight down. Projectile motion is literally a combination. The object is going to start being launched from the cannon, and obviously it's being launched as shown here, being launched to the right. So it's going to move to the right, but what happens is as it moves to the right, it is also going to undergo free fall motion. So as it moves forward, it is going to fall at the same time. So imagine I were to treat this like a graph, like these are my x values and these are my y values. The actual motion I'll see here would be plotting both of these points. So imagine here it's at a horizontal distance of whatever that would be, but it would also fall to this distance. So I can treat that motion to be right there. That object would be right at that point as it falls. Again, the next point would be it moved forward, again, a constant distance because there's no forces acting on it, but then it's going to fall down again, so that object would be located right here. And if I continue to plot these points by looking at the horizontal and vertical distance as it falls, I can chart its motion and notice that if I were to connect all these dots from start to finish, that's the path that it would take. Okay? So this is the actual path it'll take, and all it is a combination of horizontal motion, assuming Newton's first law that the forces are balanced and it would just continue to move, and it's a combination of free fall motion, and what we get is this actual path that it would take, which is the result of it moving forward and falling down. So understand at each point along its path, the horizontal speed that it would have is always going to be the same because there's no forces acting on it. But in the downward direction, we're going to see that the object is going to speed up like it did with free fall, And we also know that if we remember back to free fall, as it speeds up, it's going to accelerate at a rate of -10 meters per second each second. So we got a little bit of constant speed going on here, and we also have that it's gaining speed because of gravity. So again, two-dimensional motion, why this is a little bit tricky is that we have, because of forces, we have two different types of motions going on in each individual direction. In the horizontal direction, we see here that it's constant, and in the vertical direction, we see that the object is speeding up. All right, so this table, our first example, just kind of fill this out. This is kind of putting everything together. So in the horizontal direction, in terms of forces, there are no forces present, which means that the object, if there are no forces, is not going to accelerate. And if it's not accelerating, that means it's going to be moving at a constant speed, okay? So that's kind of what's going on there in a horizontal direction. So understand that horizontal, fancy way of saying right or left, depending on where it's being launched. Vertical direction, we're looking at up versus down. We have a completely different motion going on. So it all starts again with the forces. We know that in the vertical direction, that gravity is pulling this thing downward. So we have gravity pulling downward. Now, if gravity is pulling downward, it creates what's called an unbalance of forces. So we have unbalance. And according to Newton's second law, if it's unbalanced, the object is going to accelerate. And what we talked about back with free fall motion is going to accelerate due to gravity, which causes it to accelerate at that rate of -10 meters per second every second. And therefore, if it's accelerating, that means the velocity is changing. So going back to free fall, we know that as it falls, it's going to speed up, and as it rises up in the air, it's going to slow down. So each individual direction, horizontal or vertical direction, we have two different things going on, which is why it's important to understand two-dimensional motion. We're going to separate things into those individual directions and analyze them separately. So let's say in example 2, I have a rescue plane that's going to drop a relief package while it's moving at a constant horizontal speed and an elevated height. So assuming that the air resistance is negligible, where will it land? So this is kind of understanding the path it will take. So know that this plane is traveling at a constant horizontal speed and that the package is being launched from this position right here, okay? Another thing to keep in mind within this problem is that states in here that air resistance is going to be negligible. So if there was air resistance, that's going to cause this to be slightly different. So throughout this next couple sections, when we talk about projectile motion, to make our life easier, we are going to simply ignore air resistance. So what happens that as this thing is being dropped, okay, that if we think about it being dropped, as it drops, it's obviously going to gain speed as it falls, and it eventually will fall towards the ground. So if we think about it falling, we know that that object would fall straight towards the ground. But as it falls, it is also, because it's attached to the plane, it is also moving forward at a constant speed. Okay, so I'm going to draw these black dots to show it being at a constant speed. So I know that its motion is going to be a combination of these two things, constant speed in the x direction and speeding up as it falls. So if I were to kind of plot these points, I'll show it in blue. It would start here, and then it would be there, and then there, and then there, and then lastly be about right there. So if I were to pick the one that matches best, and I know my picture's a little bit off, but B is where it would land, okay, because it's going to go forward and fall at the same time. So again, it's going to follow that projectile path as it goes towards the ground. So the key thing here is that notice that as the plane continues to move forward, that package would still stay below the plane because it is still moving forward. The only difference is that it's moving down. Okay, and you can experience this that if you're driving in a car and you drop something while you're in the car, that thing is going to appear to fall straight down, and that is because it is already moving forward as it starts to fall down. Okay, so conceptually it's pretty simple. It's pretty straightforward of things we've already talked about. So what we're going to do is make those connections and actually get a little bit mathy with it. So what we're going to do is we're going to look at the relationship between that motion as it moves forward and as it falls towards the ground. So the two things we're going to look at is the relationship between height as it falls and then also the horizontal distance as it falls. So the height as it falls is going to look at that vertical distance as it's going throughout its motion. Again, the vertical distance is going to be affected by gravity. But what this equation is doing is it's relating the height of the object over certain amounts of time. or that value of g, just remember that g is that value of gravity, which is always that negative 10 meters per second every second. So what this is going to do is it's going to relate the height of the object or the vertical distance after a certain amount of time. Okay, so that would look at, if I'm going to show this diagram here, that would look at the vertical distance. So again, it's going to track where that object is after certain points in time. Okay. This might, for some of you might remember, this is actually one of the kinematic equations we did a while back. This is that VIT plus 1/2 AT squared, if you guys remember back. So all this is a simplified version of that kinematic equation, but we're just using this in terms of the height and time, the variables we're using for projectile motion. Second thing we're going to look at is what's called the range. So the range is, whoops, typo there, sorry folks. The range is actually going to look at not the vertical distance, but we wanted this to be the horizontal distance. My fault there. So range is going to look at the horizontal distance it travels over a certain amount of time. So understand that horizontally, okay, that's going to look at from side to side. It's going to represent how far this object moves forward. So again, tracking this motion would start at the beginning, and it would go to here, and here, and here, and here. So we should again recognize is that the spacing between these dots horizontally is going to be constant. So that's why this is a much simplified equation. But R stands for range. That's going to be how far it goes. V is going to represent that horizontal velocity. Let me write that down. So V is going to equal the horizontal velocity, and that's going to be the component of that velocity in that forward direction. And then T again represents the time. Okay, so we can have a time of 0 to 1, 2, 3, 4, and 5. Again, the time is going to represent how much time it's actually in the air. Understand that in this equation, T, time, is the same as the T in the other equation. So the one thing that does not depend on direction is time. The time is going to be the same for both equations. Okay, so this first example is looking at an example of free fall. So it says analytical drops a ball from rest at a height of 78.4 meters. So understand that this one's just going to be just a review on free fall motion. So again, she's dropping it from a cliff. So let's say that the cliff here, I'll draw a quick little picture. There's our cliff. Here's analytical. That's got a long neck. And she's dropping a ball from that cliff, and that ball is going to fall. And understand that as it falls, it's going to start to pick up speed. So I'll show this as the distance between those spots gets shorter. So we know that here it's 78.4 meters, which is going to be the height of that ball. And I want to know how much time will it take. So how much time will it take to reach the ground? And we'll worry about that second question in a second. Okay, so we're going to use that height equation. So again, the equation of height, H equals 1/2 gt squared, is going to relate the height of this object at certain points of time. So if I know the height of 78.4 meters, okay, I know that that value is going to go into my equation for H, 78.4, and my goal is to figure out the time it takes to reach the ground. Okay, so when it reaches the ground, I know that that value of g is going to be 10. Okay, now technically it's negative 10, but I don't want to have to worry about that negative, so I'm just going to put 10 in here. My goal is to solve for t. Okay, so in solving for this, what I'm going to do first is do half of 10, just simplify that. So I have 78.4 equals 5t squared. Then my goal is to solve for t. So to solve for t, what we're going to do is get rid of everything else other than the t. So I'll start off first by dividing both sides by 5. And that should give you about 15.68. And then lastly, if I want to solve for t, to get rid of that square, what I'm going to do is the square root. So very similar to what we were doing with Pythagorean theorem. So t would equal then the square root of 15.68. And that's going to give me about 3.959 seconds. So we're going to round that to about 4 seconds. So it's going to take us about 4 seconds, not us, but the ball. It's going to take about 4 seconds for that ball to reach the ground. Okay. Now, what next question says, what height will it be? And what height will it be at each of those individual seconds? So what height will it be at each second of its motion? So understand if it's in the air for about 4 seconds, we'll just make a little table here. So we'll say time and we'll say height. So I know that at 0 seconds, we know it's going to start off at 78.4 meters. We know that at 4 seconds, it's going to be at 0 meters because that's when it hits the ground. So we want to know when it's going to be at 1 second, 2 seconds, and 3 seconds. So to figure out this, again, we're going to use our same equation we did before. We're going to use the height equation based on the time. And all we got to do is just plug in these values of time where t is, and our goal is to solve for h. Okay, so I'm going to pause the video real quick. If you guys want to plug those values in, practice using that equation. Otherwise, we'll punch those in and we'll kind of track the height as it goes through. Okay, so take a look here. So the values I got would be 73.4, 58.4, 33.4, and 0 is where it again would be at the end. So values are going down. Now when you plugged into the calculator, you would have got these numbers in red. So understand what I did is that if this was my original height of 78.4, about 80 meters or so, that after 1 second it would have fallen 5 meters, so I subtracted to get that. After 2 seconds it would have fallen 20 meters, so I subtracted to get that. After 3 seconds it would have fallen 45 meters, so again I subtracted to get that. And then lastly, after 4 seconds it would have fallen about 80 meters, so that's again, we rounded this number, but subtract 80 from that would put us at 0. So again, this we rounded, it was about 3.95 if you remember, so there was a smidge of extra time there. But what I get is got these numbers and I subtracted from our original height. So recognize this pattern, goes down 5, then down 10, then 25 and 80. So that's kind of a common pattern we're going to see as an object undergoes this type of motion. Okay, sorry, sorry first of all about the problem. Realize that the problem that's in your notes is a little bit of a typo. Oopsie daisies. So make sure this is the problem you have. You're going to have to just add a couple things to it. But let's say that we have a cannonball launched horizontally at 25 meters per second from the top of an 80-meter high cliff. It's going to be similar to the last problem, except I use 78.4. So now we'll use 80 just to make it a little bit easier. And I want to know how much time will it take the ball to reach the ground. So again, how much time will it take for the ball to reach the ground? And the second part is, what is the range of the ball? So this is going to now be using both equations. So just kind of draw a picture of what's going on here. Again, we have a 80-meter tall cliff. So in the last problem I used 78.4. That's okay. So let's just imagine this cliff being 80 meters. And we have a cannonball being launched horizontally. So I'm not going to draw the cannon, but here's a cannonball being launched horizontally. Now, horizontally means straight to the right, and it's to be launched at a speed of 25 meters per second. So again, as it goes through this motion, what we're going to see is as it moves to the right, it's going to be moving at a constant 25 meters per second. And then we also know that as it does that, it's going to fall at a certain rate. Again, and as it falls, it's going to get further and further until it hits the ground. So combined motion we're going to see is that the object is going to move forward and fall, move forward and fall, move forward and fall, move forward and fall. So we're going to see its resulting motion from start to finish looks something like that. So again, I want to know the time it takes to reach the ground, and then I also want to know what is the range of the ball as it falls towards the ground. So for the time, we're going to use our height equation. I know that this right here, the value you're given is the height, so I can use the 1/2 gt squared to find the height. I know my height is 80 meters, so I'm going to take half of g, which is 10, and I'm going to try and find the time squared. So that's going to tell me the time it's going to take to reach the ground. So again, if I take half of 10, it's going to give me 5. If I take then and divide both sides by 5, that's going to give 16, and then t squared will be left over here. And then lastly, if I square root both sides, I'll know that t is going to be 4 seconds. Okay, so I get a nice clean 4 seconds. Last problem we rounded that, but now using the whole number of 80, we're going to exactly 4 seconds. So if it takes 4 seconds to reach the ground, what's the range it's going to reach? So for the range, what we're going to use is the range equation. So r equals v times t. So to find the range, r, v, we're going to use the speed at which it was launched. So in this case, it's launched at 25 meters per second horizontally. So understand that this is the speed that we are going to use, and since it's horizontally, that's the speed we're going to use in that direction. So I'm going to do 25 times the amount of seconds, which is going to be 4 seconds. So I know that every 25 meters per second literally means that every second is going to travel 25 meters. So if we're allowed to travel for 4 seconds, that means it's going to travel 100 meters. So this object would go 100 meters forward before it hits the ground. So this is kind of making the connection. We have what's going on in the vertical direction versus what's going on in the horizontal direction. Two different things because the motion is treated separately in each of those. All right, so I know there's one more example that you're going to go through. I'll save that one for class. If you have any questions, again, jot those things down. Again, sorry about this problem here. Forgot to fix it in your notes. So go ahead and write down any questions you have. We'll go through some more examples like this.